All right, now we're ready to actually solve the problem. So with the Newton's second law problem, we always do free body diagrams. And because there are 3 objects, we're going to need 3 free body diagrams. So I'm going to start out with mass 1. My first step of the free body diagram process is going to be to isolate the body. So I'm just going to draw a simple box. Step 2 is our 1-TEF mnemonic. Draw and label all external forces acting on the body. So in this case, there's a weight force for mass 1, and then a tension force for mass 1. And I can't state that the tension force for mass 1 and mass 2 are the same because the pulley has mass. Therefore, I gotta use some subscripts. Step 3 is draw a coordinate axis. So I'm just gonna say that it's positive y going up. And then step 4 is always draw and label our critical angles and critical dimensions on the free body diagram. There are no critical angles here for mass 1. So that means I can move on to mass 2. I do the same thing. I'm going to isolate the body. Mass 2, the weight force is labeled. I start from the center of mass and point downward. And the tension force for mass 2 is pointing up. But now I'm going to rotate that's the extent of my forces. Now I'm going to rotate that coordinate axis so that the y direction is pointing down, the x direction points to the left. Again, there are no critical angles here. All the forces go in either 90 degrees or 180 degrees or 0 degrees. In this case, they're all going in the y direction. They're not off of the coordinate axes at any point. So I don't have to draw a critical angle. So that means I can do the free body diagram for the pulley. So I'm going to draw a couple circles, a little bit different. Do my best to make them look concentric. That's pretty good. So then I'm going to draw my axes of rotation. So in this case, I've isolated the pulley. I isolated the body of the pulley. And then now I'm going to draw and label all my external forces acting on it. So I have a weight force. We said that the pulley has mass, so that's MP times acceleration due to gravity. And then I know there's going to be a normal force on the pulley, but I'm going to wait till I draw my other forces first. So next up, I'm going to do my tension force. Just like this. T1, pointing downward, and then on the smaller circle is T2. Labeled there. There's no friction, and then there's no other applied forces acting on the pulley. So my normal force for the pulley is always opposite in direction of the summation of all the other forces. So in this case, since all the other forces point downward, the normal force of the pulley must be pointing up. And now I'm ready for step 3, which is again draw my critical angle. Not critical angle, draw my coordinate axes, and then I'm also going to draw and label direction of positive rotation. And I just pick a direction of positive rotation. It doesn't matter which way. In this case, I'm saying, hey, clockwise is going to be positive, and that's fine as long as it gets to the solution. The key thing about it is if you say that positive rotation is clockwise or counterclockwise, you just have to follow through with your work. You can't go back and start messing that up. You have to make sure you match that coordinate axis, otherwise you're going to get the wrong answer. So because I said positive is going clockwise, got to follow through with my work. All right, so now I'm ready for that final step of the free body diagram process. In this case, it is draw and label critical angles, draw those critical angles and critical dimensions. Well, there are no critical angles. All the forces go in the y direction or negative y direction, but there are definitely critical dimensions. So critical dimensions are those distances from forces that are not starting from the axes of rotation. So my normal force and weight force for the pulley, they all start at the axes of rotation, but my tension force of the pulley does not. It starts some distance away and from the axes of rotation to the point of application of the force. So I'm going to label that as R1. And then I also have a critical dimension for T2, where it's a distance away from the axis of rotation to the point of application of tension force 2. All right, so that gives us, it's important to label those critical dimensions because that means that those forces, T1 and T2, they're going to create some torque. So that's what I'm going to look at later on when I go into the rest of Newton's second law. Okay, so now that's what I'm ready for. So once I have these free body diagrams, now I'm going to write out Newton's second law. So I do it both for translational motion and then rotational motion. So sum of all external forces, which is a vector, is equal to the object's mass times its acceleration. Then over to the right, I'm going to write the summation of all external torque is equal to the rotational inertia of an object times its angular acceleration. All right. Now, with vectors, I'm going to resolve that out into x and y, but for both mass 1 and mass 2, there is no forces in the x, so I'm only going to resolve it out into the y. So the summation of all the external forces of mass 1 is equal to, in the y direction for mass 1 is equal to mass 1 times its translational acceleration or linear acceleration of mass 1 in the y direction. Then I also have the summation of all external forces in the y direction for mass 2 is equal to mass 2 times its linear or translational acceleration of mass 2 in the y direction. And notice I'm not doing this for the pulley, and that's because the pulley does not actually move translationally. It's only rotating. It's not like the pulley's shifting up and down or left and right. So we're just it's maintaining its position on that axle. So I don't have to do Newton's second law in this case for the pulley, for translational motion. So I am going to list out my forces in the y direction for mass 1. So I have T1, which is pointing in the positive y, minus the weight force of mass 1. All that's going to be equal to mass 1 times its translational acceleration in the y direction. And then I do the same thing for mass 2, except in this case, the weight force is actually going in the positive y direction according to my coordinate axes, and I maintain my coordinate axes, minus tension 2, which is going in the negative direction. All that's going to be equal to mass 2 times the acceleration of mass 2 in the y direction. And then that brings us now to our torque equation. Okay, so in the case of torque, I'm looking for those forces that are going to cause it to rotate. So remember, torque is equal to, and is a vector, is equal to the rotational inertia, the torque is equal to the position vector cross product with the force vector. So for my problem, normal force and the weight force of the pulley, they don't have a position vector. The magnitude of the position vector is going to be equal to 0. And so in that case, there's going to be no torque from them. But there's definitely going to be torque for tension 1 and tension 2 because we know what the magnitude of those position vectors are. That's our R1 and R2 value. So I'm going to list out torque 2 and torque 1. So torque 2, if I use my right hand rule, I curl my fingers, it's going to want to, torque 2 wants to pull the pulley down clockwise. So that means that torque 2 is going to be positive. But torque 1, the torque from tension 1, is going to be negative. It wants to pull the pulley counterclockwise. And all that's going to be equal to the rotational inertia of the pulley times the angular acceleration. So I can do my little cross product. So I have the magnitude of torque 2, which is R2, times the magnitude of the tension force of tension 2, which is tension 2. And that's going to be sine of theta. In this case, that theta is equal to 90 degrees. So I'm going to erase this theta symbol. I'm going to put 90 degrees on there. All right. And then I'm going to do the same thing for torque 1. So the magnitude of my position vector for torque 1 is equal to R1 times T1 times, again, it's going to be 90 degrees because tension forces are always tangent to the pulley, the circle of the pulley, which gives us that nice 90-degree angle. Okay, so sine of 90 is equal to 1, so that's nice there. All right, so now I'm going to highlight, one thing here. In this case, we're going to use this color. All right, so I don't know my T2 value, and I don't know this T1 value. But if I look over here, I can solve for those variables pretty easily, and then I can substitute them into my equation there, because my goal at the end is to determine and write an algebraic expression for that angular acceleration. So I'm going to do that now. I'm going to solve for T1, and then I'm going to have to do a conversion. That translational acceleration of mass 1, I'm going to convert that actually to angular acceleration. So that means I have angular acceleration times r1 using that link equation way up here. I'm going to use that equation right here to go and substitute it in. Boom. So now I have an equation for T1. Then I'm going to do the same thing for tension 2. So I am given, I do this and resolve it out. This looks pretty good there. All right, so now I'm ready to combine equations in order to actually solve for that angular acceleration. So I'm going to label these equations as equation 1, equation 2, and this is 3. So equation 1 plus equation 2 goes into equation 3, and that's going to give us equation 4, where we're actually going to solve for that angular acceleration. So I'm going to substitute in first my tension 2. So r2 times mass 2 times acceleration due to gravity minus mass 2 times acceleration, angular acceleration times r2. And then I'm going to minus r1. Oh, I definitely got to make sure I remember that parentheses symbol. All right, so I'm going to minus r1 times t1, which is mass 1 times angular acceleration r1 plus mass 1 times acceleration due to gravity. And all that's going to equal the rotational inertia of the pulley times its angular acceleration. Okay, now I'm going to factor in this r2 and r1 value. So I'm going to simplify my equation a little bit. So now I got r2 squared. Then I'm going to remember this minus sign. Make sure I don't forget that. And then I go through accordingly, which I did. So I'll erase it. Notice I didn't factor in that negative sign, so now I'm going to fix that real quick. All right, all that's going to be equal to the rotational inertia of the pulley times its angular acceleration. Okay, so the quantity I'm looking for is angular acceleration for part A. So I got all of these nice angular accelerations. I'm going to combine them all together. I'm going to put them on the left-hand side and then put everything else on the right-hand side. So I have the rotational inertia of the pulley times angular acceleration plus mass 1 times angular acceleration r1 squared plus mass 2 angular acceleration r2 squared. All that's going to equal mass 1 times rotation, acceleration due to gravity r1 minus mass 2 acceleration due to gravity r2. Okay, so now I just factor out that angular acceleration, put everything else in big parentheses. Then we have this. I'm going to keep the same stuff on the right hand side and close my parentheses. All right, and now I can do one final step where the angular acceleration is equal to mass 1 times acceleration due to gravity r1 minus mass 2 acceleration due to gravity r2, all that divided by the rotational inertia of the pulley plus m1 r1 squared plus m2 r2 squared. Phew! We made it, physics fans. We created an algebraic expression for angular acceleration of the pulley. Now, I'll leave you to it to actually substitute in values. Just note that for angular acceleration, your units are going to be radians per second squared. And that we're dealing with 1 sig fig for our final answer. Once you have that angular acceleration, then you can solve for the linear accelerations for each weight. All right, physics fans, good luck.